Every diagram you have ever seen of the solar system is missing something critical. Those flat textbook illustrations floating in black emptiness never show you what actually exists directly above your head and directly beneath your feet at galactic scale. The answer is not nothing. Approximately 55 light-years above the midplane of the Milky Way, our entire solar system is embedded inside a galactic disk, roughly 1,000 light-years thick, surrounded by ancient stars, hot gas, wandering globular clusters, and a massive halo of dark matter stretching hundreds of thousands of light-years in every direction. The real shock is not what is out there. It is how completely wrong your mental picture of where you live has been your entire life. If you want to finally see where the solar system actually sits in three-dimensional space, consider hitting that like button and subscribing. It genuinely helps this channel keep exploring the strangest truths in our universe, and we never take that support for granted. Now, settle in and get yourself comfortable. Let's begin. Close your eyes and picture the solar system. You already know the image. A yellow circle sits in the middle. Rings of orbits fan outward around it, each one carrying a planet at a tidy distance from the Sun. Mercury hugs the center. Venus comes next. Earth takes the third ring. Mars, Jupiter, Saturn, Uranus, Neptune follow in order, all arranged on the same flat surface like grooves on a vinyl record. The background is black, pure, featureless, absolute black. Nothing exists above the diagram, nothing exists below it. The planets orbit in a clean plane, and beyond the outermost ring the darkness simply continues forever in every direction. Without structure, without orientation, without meaning. That image lives in your head right now. It has lived there since you were a child. You saw it on classroom posters, in glossy textbook pages, on science television programs, in museum exhibits, and on countless websites. It is the single most reproduced diagram in the history of science education, and it is lying to you in a way that most people never notice. Not because the orbital positions are wrong, they are roughly correct. Not because the planet order is incorrect, it is accurate. The lie is far more fundamental than that. The lie is everything that the diagram leaves out, and more importantly, it is the false assumption the diagram plants in your mind about what surrounds the solar system in every direction, including the two directions you have almost certainly never thought about. Up and down. That flat orbital diagram is presented in isolation. It floats against a blank background because the illustrator needed a clean image, because the textbook chapter was about planetary orbits, because there was no room on the page to show the larger context. Fair enough. Graphic design has constraints, but the human brain does something dangerous with that blank background. It interprets the absence of information as information itself. When you see the solar system floating in blackness with nothing above and nothing below, your brain does not file that image with a footnote that says context was omitted for clarity. Your brain concludes, quietly and permanently, that the blackness is real, that the solar system genuinely floats in a directionless void, that above and below, the orbital plane are meaningless directions pointing into infinite nothing. This is wrong. Spectacularly, structurally, fundamentally wrong, and the reason it matters is that it prevents you from understanding where you actually are. Think about how maps work on Earth. If someone handed you a street map of your neighborhood, you would understand instantly that the white space at the edges of the map does not represent a void. You know your neighborhood connects to other neighborhoods, which connect to cities, which connect to states, which connect to continents. The map simply chose a boundary and stopped drawing. Your brain fills in the rest because you already carry a mental model of Earth's geography. You have seen globes, atlases, satellite images. You understand that the map is a cropped excerpt from a much larger territory. Now consider the solar system diagram. When the textbook draws that flat orbital picture and surrounds it with black, most people have no larger mental model to fill in. They have no intuitive sense of the galactic geography, that the solar system connects to. They have never seen the equivalent of a globe or atlas for the Milky Way, drawn from the solar system's perspective. So the black background becomes the final word. The emptiness sticks, and a false picture of cosmic isolation lodges itself in the human imagination so deeply that most people never question it for the rest of their lives. But there is something specific that the diagram hides, and it is not just that space contains other objects. The deeper problem is that the solar system has an orientation. It is tilted. It sits at a specific angle inside a much larger structure, and that structure has a definite vertical dimension. Once you know about that orientation, the words above and below stop being meaningless. They point somewhere real. They point into a layered galactic environment that is as physically concrete as the ground beneath your feet, even though no human eye has ever perceived it directly. Here is what the textbook never told you. The solar system does not float alone. It is embedded inside the disk of the Milky Way galaxy. Not beside it, not near it, but inside it, like a single grain of flour suspended in the middle of a vast, flattened loaf of bread. The Milky Way is a barred spiral galaxy roughly 100,000 light-years across, but it is not a sphere, it is a disk. A relatively thin, rotating disk of stars, gas, dust, and dark matter. Near our location, that disk measures approximately 1,000 light-years thick. 1,000 light-years is an enormous distance by any human standard, but compared to the disk's diameter, it is remarkably thin. The ratio is roughly 100:1. If you scaled the Milky Way down to the size of a dinner plate, the disk would be thinner than a sheet of paper. The solar system sits inside that paper-thin disk, not at the center, not at the edge. Roughly 26,000 light-years from the galactic center, positioned within a minor structure called the Orion Arm, one of the galaxy's spiral features. And here is the detail that changes everything. The flat orbital plane of the planets, that familiar diagram you carry in your head, does not align with the flat plane of the galactic disk. The two planes are tilted relative to each other by approximately 60 degrees. 60 degrees is a steep angle. Picture a ramp tilted so sharply that you would struggle to walk up it. That is the angular relationship between the plane of Earth's orbit around the Sun and the plane of the Milky Way's disk. The solar system is not lying flat inside the galaxy like a coin on a table. It is cocked sideways, dramatically tilted, so that the directions perpendicular to the planetary orbits do not align with the directions perpendicular to the galactic disk at all. When you look straight up from the North Pole of the solar system, you are not looking straight out of the galaxy. You are looking diagonally through the galactic disk at a steep angle. And when astronomers talk about what exists above and below the solar system in galactic terms, they do not mean above and below the orbital plane of the planets. They mean above and below the galactic midplane, the central horizontal sheet of the Milky Way's disk itself. This distinction matters enormously, and almost no popular science source makes it clear. There are two different up directions in play. One is perpendicular to the ecliptic, the plane in which the planets orbit. The other is perpendicular to the galactic plane, the disk of the Milky Way. These two directions diverge by 60 degrees. When we ask what exists above and below the solar system, we are asking about the galactic vertical, the direction astronomers call galactic north and galactic south. These directions point out of the disk of the Milky Way, away from the dense central sheet of stars, gas and dust, and into the layers of increasingly sparse material that extend thousands and eventually hundreds of thousands of light years above and below the galactic midplane. Those directions are not empty, they are not featureless, they are not void. They contain real, mapped, observed structures, and those structures tell a story about where we are that the flat textbook diagram could never convey. But before we look in those directions, we need to understand why human intuition fails so completely at this task. Why does it feel natural to imagine the solar system floating in nothing? Why does the idea of galactic above and below feel strange, almost forced, as though someone invented those directions artificially. The answer is evolutionary. Human brains developed on the surface of a planet where up and down are defined by gravity. You feel the pull of Earth beneath your feet. You know which direction is up because your vestibular system tells you, because dropped objects fall, because the sky is above and the ground is below. This orientation is hardwired into your perception of reality. It is so fundamental that you do not think about it. You simply experience it. Now remove gravity from the equation. Float in open space and the concepts of up and down dissolve. Every direction looks the same. The stars scatter uniformly around you. There is no floor, no ceiling, no horizon. In this environment, the idea that one direction might be more meaningful than another feels absurd. And this is exactly the mental state that most people enter when they think about the solar system. They unconsciously strip away all external reference frames and imagine the sun and planets floating in a gravity-free void where orientation is meaningless. The problem is that orientation is not meaningless. It only feels meaningless because the relevant reference frame is invisible to the naked eye and operates at a scale that dwarfs human perception. The Milky Way's disk defines a plane. That plane gives the galaxy a top and a bottom, a galactic north and a galactic south. The sun orbits within that plane. The solar system bobs gently above and below the midplane over millions of years. The galaxy's vertical structure, its thickness, its layered composition, its halo of ancient stars and dark matter, all of this provides a reference frame as physically real as Earth's gravitational field. You simply cannot feel it. You cannot see it when you look up at the night sky. Or rather, you cannot see it unless you know what to look for. Because the evidence is there, visible on any clear, dark night, and it has been there for the entire history of the human species. The Milky Way band stretching across the sky is the edge-on view of the galactic disk seen from inside. That glowing river of light is not decoration. It is the disk itself, the dense central sheet of stars, gas and dust that the solar system is embedded within, projected onto the sky as a band, because you are looking along the plane rather than through it. When you face the Milky Way band, you are looking horizontally through the disk, and the accumulated light of billions of distant stars merges into that pale glow. When you look away from the band, perpendicular to it, you are looking vertically, out of the disk, into the sparse regions above or below the midplane. This contrast is visible to the naked eye, and once you know what it means, it is striking. Look toward the constellation Sagittarius on a summer night, and the Milky Way band is at its broadest and brightest, because you are looking toward the galactic center, where stars pack most densely. The sky in that direction is so crowded with distant suns that the glow is visible even from moderately light-polluted locations. Now turn 90 degrees and look toward the constellation Coma Berenices, high overhead in the spring. The Milky Way band is nowhere near that part of the sky. The stars thin out dramatically. The region looks sparse, dark, comparatively empty. You are looking straight out of the galactic disk toward galactic north, away from the dense midplane, through the thinning upper layers of the thin disk and into the even sparser regions beyond. That dark, star-poor patch of sky is not empty. It is the direction where the thick disk, the stellar halo, the globular clusters, the gaseous halo, and the dark matter halo all extend outward for hundreds of thousands of light years. The emptiest looking part of the night sky is actually the direction with the deepest vertical structure. The brightest part, the Milky Way band, is just the dense midplane seen edge-on. Every clear night, you are staring at the evidence that the solar system has a meaningful above and below defined by the galaxy, and most people never realize what they are seeing. The band is the disk. The darkness away from the band is the vertical. The contrast between them is the three-dimensional structure of the galaxy, written across the sky in naked-eye starlight. This is the core failure of the textbook diagram. It does not just omit the Milky Way for simplicity. It actively trains your brain to think of the solar system as a self-contained object with no external structure worth depicting. It conditions you to believe that the solar system ends at Neptune, or maybe at the Kuiper belt, or perhaps at the outermost wisps of the Oort cloud, and that beyond those boundaries lies a uniform darkness extending equally in all directions. This uniformity is an illusion. The space above the galactic midplane is different from the space within the midplane. The space below is different again from the space at the edges of the disk. The solar system is not surrounded by featureless symmetry. It is immersed in a structured environment where direction matters, where vertical position within the disk determines what kinds of stars, gas, and gravitational influences surround you. Consider an analogy that might make this click. Imagine you live in a submarine, floating in the middle of the ocean. You have spent your entire life studying the interior layout of the submarine. You know every room, every corridor, every mechanical system. You have detailed diagrams of the vessel pinned to every wall. But every diagram shows the submarine in isolation, floating in blank blue, with no indication of depth, no seafloor beneath, no surface above. One day, someone tells you that the submarine is floating at a specific depth in a structured ocean, that above you, the water becomes warmer, lighter, and eventually gives way to air and sky, and that below you the water grows colder, darker, heavier, and eventually meets a seafloor covered with geological features you have never imagined. Your entire understanding of where you are shifts. Not because the submarine changed, but because you finally learned about the medium surrounding it. That is what is about to happen with the solar system. The submarine is fine, the orbital mechanics are accurate, the planets are where they should be, but the medium, the galactic environment that the solar system is embedded within, has a vertical structure that most people have never been shown. And once you see it, the flat diagram will never look the same again. The Milky Way's disk is not a single uniform slab. It has internal layers. The most prominent division, confirmed through decades of stellar surveys and dramatically sharpened by the European Space Agency's Gaia mission, separates the disk into two components. The thin disk, where most of the galaxy's young stars, gas clouds, and active star formation reside, measures roughly 1,000 light-years in thickness near our position. The solar system lives inside this thin disk, slightly above the geometric center, but surrounding the thin disk is a second, puffier structure called the thick disk. This component extends 2,000 to 4,000 light-years above and below the midplane, roughly 3 to 4 times the height of the thin disk. The thick disk is composed almost exclusively of older stars, many of them 7 to 10 billion years old, with chemical compositions that set them apart from their thin disk neighbours. These stars contain fewer heavy elements, forged in an earlier era of galactic history when the Milky Way was younger and less chemically enriched. Already, you can see that the space above and below the solar system is not empty. Within just a few thousand light-years of the midplane, you transition from the young, active thin disk into the older, quieter thick disk. The stellar population changes, the chemistry changes, the density changes, the character of the galactic environment shifts, and you have barely left the disk at all. But the structure does not stop there. Beyond the thick disk, extending tens of thousands of light-years above and below the midplane, lies the stellar halo. This is a roughly spherical cloud of extremely old stars and globular clusters, ancient gravitationally bound balls of hundreds of thousands of stars that orbit the galaxy in long, looping trajectories. The stellar halo is sparse. Its stars are scattered across enormous volumes. If you could stand on a planet orbiting one of these halo stars, the night sky would appear dramatically emptier than the sky seen from Earth, because so few neighbouring stars would be close enough to see. The halo is a ghost population, remnants of the Milky Way's earliest formation and of smaller galaxies that were devoured and dismantled over billions of years. And beyond even the stellar halo, extending to distances that may reach 500,000 to 1 million light-years from the galactic center, lies the dark matter halo. This invisible structure contains roughly 10 times more mass than all the visible stars, gas and dust in the galaxy combined. It cannot be seen with any telescope. It emits no light, absorbs no light, reflects no light, but its gravitational influence is real and measurable. It shapes the orbits of stars in the outer galaxy. It governs the movements of satellite galaxies like the Large and Small Magellanic Clouds. It defines the true gravitational boundary of the Milky Way, extending the galaxy's reach far beyond what any optical image could suggest. This is what exists above and below the solar system. Not nothing, not featureless void, not blank blackness. A layered, structured, three-dimensional environment that transitions from the dense young disk through the older thick disk into the ancient stellar halo, and finally into the dark matter scaffolding that holds the entire galaxy together. Each layer has different stars, different chemistry, different ages, different densities. Each layer tells a different chapter of the Milky Way's history, and every single one of these layers exists in the directions that the textbook diagram told you were empty. The solar system sits approximately 55 light-years above the galactic midplane right now. That is not a permanent address. The Sun oscillates through the disk as it orbits the galactic center, bobbing above and below the midplane in a slow cycle that takes tens of millions of years to complete. Right now, we are slightly above the midplane and still rising. This oscillation means that the solar system's vertical position within the galaxy is not fixed. It is a slow, ongoing journey through changing environments, and we will explore exactly what that journey looks like shortly. But here is the fact that should stop you cold. Right now, at this moment, you are sitting on a planet orbiting a star that is embedded inside a galactic disk, tilted 60 degrees relative to the plane of the planets, surrounded by a vertical column of galactic structure extending hundreds of thousands of light-years above your head and hundreds of thousands of light-years beneath your feet. You have lived your entire life inside this structure. Every human who has ever existed lived inside this structure, and yet the most common image of the solar system, the image printed in millions of textbooks and displayed on millions of screens, shows none of it. The diagram gives you a flat set of orbits and a black background, and your brain accepts the black background as a description of reality rather than an admission of omission. The blank space on the diagram is not emptiness, it is ignorance, and what fills that space, once you know where to look, is a galactic architecture so vast and so layered that the solar system shrinks from the centerpiece of a chart into a barely visible speck inside something enormously more complex than you were ever shown. What comes next is the full three-dimensional picture, the galactic plane, the solar system's precise address within the Milky Way, the recently discovered structures in our local neighborhood that astronomers are only now mapping for the first time. Once you see the real framework, the flat diagram does not just become incomplete, it becomes almost unrecognizable as a picture of the same place. To understand what exists above and below the solar system, you first need something most people have never been given: a proper address. Not Earth's mailing address, not the solar system's position in a line of planets, but a genuine three-dimensional location within the Milky Way galaxy, expressed with enough precision that you could point in real directions and say with confidence, "That way is the galactic center, that way is the rim, that way is galactic north, and that way is galactic south." Without this coordinate system, the phrase above and below the solar system remains vague. With it, those words become as concrete as north and south on a compass. Start with the galactic plane itself. The Milky Way is a rotating disk of matter, and like any spinning disk, it has a well-defined central surface. Astronomers call this the galactic midplane. It is the geometric center of the disk's vertical profile, the line of symmetry around which the galaxy's mass is most densely concentrated. If you imagine the Milky Way edge on, the midplane is the bright horizontal stripe running through the middle of the disk, the densest concentration of stars, gas, and dust. Everything in the galaxy can be located relative to this plane. Objects in the midplane have a galactic height of 0. Objects above it have positive galactic latitude. Objects below it have negative galactic latitude, the direction perpendicular to the midplane pointing toward the constellation Coma Berenices is defined as galactic north. The opposite direction, pointing toward the constellation Sculptor, is defined as galactic south. These are not arbitrary labels. They correspond to real physical directions in space, defined by the orientation of the galaxy's mass distribution. When you stand outside on a clear night and locate the constellation Coma Berenices high in the spring sky, you are looking almost directly out of the galactic disk toward galactic north. You are looking up and out of the Milky Way's structure, away from the dense band of stars, into the sparse reaches above the disk. When you look towards Sculptor in the autumn sky, you are looking the other way, down through the disk and out the bottom. These two directions, galactic north and galactic south, are the directions this story is about. Now place the Sun within this framework. The solar system orbits the galactic center at a distance of approximately 26,000 light-years. This puts it roughly in the middle zone of the disk's radial extent, not at the very center, not at the far edge, but somewhere in the broad suburban belt between the dense inner regions and the sparse outer frontier. In terms of spiral structure, the Sun sits within the Orion Arm, also called the Orion Spur, a relatively minor structural feature positioned between two larger spiral arms, the Sagittarius Arm closer to the galactic center and the Perseus Arm farther out. The Orion Arm was once considered a mere bridge between these larger features, but more recent observations suggest it is a significant structure in its own right, containing major star-forming complexes and stretching thousands of light-years through the disk. The Sun's position within the Orion Arm determines what you see when you look outward in any direction along the galactic plane. Toward the galactic center, the sky is crowded with stars, dust lanes, and the diffuse glow of countless overlapping stellar populations packed into the inner galaxy. Toward the galactic rim, stars thin out. The density drops. The interstellar medium becomes sparser. This radial gradient is the horizontal story of the disk, the variation you notice when looking along the midplane in different directions. It is well known and widely discussed in popular astronomy. But the vertical gradient, the change in stellar density as you move above or below the midplane, receives almost no attention in popular science, and yet it is just as dramatic. The galactic disk is not a slab of uniform density. It has a sharp peak at the midplane and falls off steeply on either side. At the midplane itself, stars in our neighborhood are spaced an average of 4 to 5 light-years apart. Move just 500 light-years above or below, and that spacing widens dramatically as the stellar density drops. Move 1,000 light-years, and you're at the outer boundary of the thin disk, where the stellar population thins to a scattering of older, cooler stars. This vertical fall-off is exponential, meaning the density halves with every few hundred light-years of height, dropping rapidly at first and then more gradually as you enter the thick disk and eventually the halo. The Sun currently sits approximately 50 to 60 light-years above the midplane, a measurement refined by multiple studies using stellar surveys and Gaia astrometric data. That offset is small enough that the Sun is effectively within the dense central sheet of the thin disk, surrounded by the galaxy's richest concentration of young stars, molecular clouds, and interstellar gas. But even this tiny offset places the Sun slightly north of the galactic equator, a detail that becomes relevant when we consider the Sun's long-term motion through the disk. Here is where the picture gains a dimension that most visualizations never show. The Sun does not orbit the galactic center in a perfect circle confined to the midplane. It follows a roughly elliptical path around the galaxy, while simultaneously oscillating up and down through the disk, like a horse on a carousel that rises and falls as it circles the central pole. The period of this vertical oscillation is approximately 60 to 70 million years for one complete cycle, meaning the Sun crosses the midplane roughly every 30 to 35 million years, alternating between excursions above and below the disk. The amplitude of the oscillation carries the Sun approximately 200 to 250 light-years away from the midplane at its greatest vertical distance. Currently, we are in the ascending phase of this oscillation, moving upward through the disk toward our next peak above the midplane, having crossed northward through the midplane roughly 3 million years ago. This oscillation is not merely a geometric curiosity. As the Sun moves through different vertical layers of the thin disk, the physical environment changes in measurable ways. Near the midplane, the interstellar medium is at its densest. Molecular clouds, the cold, opaque nurseries where new stars are born, concentrate within a narrow layer, perhaps 300 light-years thick, centered on the midplane. Dust is thickest here too, dimming and reddening starlight traveling through the disk. Cosmic ray flux, the constant rain of high-energy particles accelerated by supernova shockwaves, is modulated by the density of the surrounding gas, which provides shielding. At the midplane, a star and its planets sit in the most shielded position, surrounded by the densest cushion of interstellar material. Climb 100 light-years above, and the gas thins. The dust clears. The shielding weakens slightly. Climb to the oscillation peak, 250 light-years above the midplane, and the environment has changed appreciably. The molecular cloud layer is far below. The interstellar medium is more tenuous. The sky in every direction is more transparent because there is simply less material between you and the rest of the galaxy. Some researchers have investigated whether these periodic passages through varying environments correlate with events in Earth's geological and biological history. The hypothesis is provocative. Every 30 to 35 million years, the solar system crosses the dense midplane and potentially encounters denser gas clouds, higher cosmic ray fluxes, or increased gravitational perturbations from the concentration of mass in the disk, any of which might destabilize the Oort cloud and send comets raining inward, or affect Earth's atmosphere and climate through increased high-energy particle bombardment. Some statistical analyses of impact crater ages and mass extinction timing have hinted at periodicities that roughly match the oscillation period. A reanalysis using updated molecular cloud data, however, has failed to confirm a robust correlation. The evidence remains inconclusive and actively debated. What is not debated is the oscillation itself. It is a measured, confirmed feature of the Sun's galactic orbit, and it means that the solar system's relationship to the vertical structure of the galaxy is not static. It is a slow, ongoing journey through layers. There is another aspect of this oscillation that is easy to overlook. As the Sun rises above the midplane and then falls back through it, it does not move through empty space. It moves through the gravitational potential of the disk itself. The mass concentrated near the midplane exerts a restoring force, pulling the Sun back whenever it strays too far above or below. This is analogous to a ball rolling back and forth in a bowl. The midplane is the bottom of the gravitational bowl, and the Sun oscillates around it because there is not enough vertical energy in its orbit to escape the disk's gravitational well entirely. Stars with more vertical energy oscillate to greater heights, spending more time in the thick disk and eventually the halo. Stars with less vertical energy stay confined closer to the midplane. The Sun's modest oscillation amplitude of 250 light-years marks it as a well-behaved thin disk citizen, never straying far from the galaxy's busy center layer. Now consider the tilt. The galactic plane does not align with the plane of the solar system. The ecliptic, the plane in which Earth and the other planets orbit the Sun, is inclined at approximately 60 degrees to the galactic midplane. This steep tilt has a direct observational consequence that is rarely explained in popular sources. When you stand on Earth and look straight up toward the ecliptic North Pole, the point in the sky directly above the plane of the planets, you are not looking toward galactic north. You are looking at a point in the constellation Draco, roughly 60 degrees away from the direction of galactic north in Coma Berenices. Conversely, when you look toward galactic north, you are looking at a direction that is steeply inclined relative to the orbital plane of the planets, cutting diagonally through the spatial framework of the solar system itself. This tilt means that the galactic vertical direction is not aligned with any obvious solar system reference. There is no intuitive reason for a person standing on Earth to associate any particular direction in the sky with the concept of galactic up. The band of the Milky Way stretches roughly along the galactic midplane. So, directions away from that band are directions away from the disk, but the band arcs across the sky at a steep angle to the celestial equator and does not align with local horizon directions at most latitudes. The result is a kind of perceptual disconnection between the observable sky and the galactic structure it contains. You can see the Milky Way band, but you cannot intuitively read it as a disk viewed from inside, and you certainly cannot look at the sky away from the band and instinctively understand that you are looking out through the layered vertical structure of the galaxy. This perceptual disconnection is a major reason why the galactic vertical remains invisible to most people's imaginations. On Earth, gravity tells you where up and down are. In the solar system, the ecliptic plane provides a local reference for above and below, but neither of these reference frames aligns with the galactic plane, so the galactic vertical has no perceptual anchor. It is a direction that exists physically but is invisible experientially. You cannot feel it, you cannot see it directly, and nothing in your everyday spatial orientation points toward it. Now zoom into the immediate neighborhood. The Sun does not sit in a typical stretch of the galactic disk. It occupies a peculiar local environment that astronomers have been mapping with increasing precision over the past 2 decades. This environment is called the local bubble, and its existence changes the picture of our cosmic surroundings in ways that are surprisingly recent discoveries. The local bubble is a cavity in the interstellar medium. It is a region roughly 1,000 light-years across, where the normal dense gas and dust of the galactic disk have been largely cleared away, replaced by an extremely low-density plasma heated to approximately 1 million degrees Kelvin. Despite that extreme temperature, the gas is so sparse, roughly 0.05 atoms per cubic centimeter, that it would register as a near-perfect vacuum by any laboratory standard. If you could somehow stand inside the local bubble without a spacesuit, you would freeze, not burn, because there are so few particles to transfer heat. This cavity was carved out by a series of supernova explosions over the past 10 to 20 million years. Massive stars in nearby stellar associations, particularly in the Scorpius-Centaurus association, exhausted their fuel and detonated, each blast sweeping interstellar material outward like a shockwave clearing debris. The cumulative effect of an estimated 15 supernovae created the bubble, a region where the interstellar medium was evacuated, compressed to the bubble's edges, and replaced by hot, tenuous gas. The Sun entered this bubble approximately 5 to 6 million years ago during its orbit around the galaxy, drifting into the evacuated zone from a denser region of the interstellar medium. It now sits near the bubble's interior, surrounded by almost nothing, at least in terms of the cold, dense gas that fills most of the galactic disk. The local bubble is not an isolated feature. It neighbours another major bubble, the Loop I bubble, associated with the Scorpius-Centaurus stellar association, roughly 500 light-years from the Sun. The Loop I bubble is driven by ongoing stellar winds and supernova activity in that young, active group of stars. Where the local bubble and the Loop I bubble press against each other, their walls interact. The local interstellar cloud, a small, slightly denser wisp of warm gas through which the solar system is currently travelling, formed at the interface between these two bubbles. The solar system entered the local interstellar cloud within the past 10,000 years and may exit it within the next 2,000. We are currently drifting through the contested boundary zone where 2 supernova-driven cavities meet. The local bubble is also not spherical. Recent mapping efforts using 3-dimensional dust surveys constructed from Gaia data have revealed an irregular, somewhat elongated shape that is narrower along the galactic plane and wider in the vertical direction, perpendicular to the disk. The bubble appears to stretch more easily above and below the midplane than it does horizontally, because the disk's gas density provides more resistance along the plane than it does in the vertical direction. This asymmetry means the local bubble may function partly as a chimney, a conduit through which hot gas from supernova explosions vents upward and downward out of the thin disk into the more rarefied regions above and below. This chimney effect connects directly to the question of what exists above and below the solar system. If you look vertically away from the galactic midplane from our current position, you are looking through a bubble that may extend farther in those directions than it does along the disk. The vertical environment immediately surrounding us is shaped not just by the galaxy's general structure, but by a local accident of stellar death and interstellar dynamics. The hot, low-density cavity above and below us is a temporary feature, cosmically speaking. In tens of millions of years, the bubble will cool, collapse, and refill with ordinary interstellar gas. But right now, in this particular era of galactic history, the solar system's vertical neighborhood is unusually empty compared to what a typical star embedded in the thin disk would experience. In 2022, a study published in Nature by astronomers at the Harvard-Smithsonian Center for Astrophysics demonstrated that all major star-forming regions within 500 light-years of the Sun sit on the surface of the local bubble, not inside it. The bubble's expanding shell swept up the surrounding gas, compressing it into dense ridges where gravity could take hold and trigger the collapse of new molecular clouds into stars. The Taurus molecular cloud, the Ophiuchus complex, the Perseus cloud, all of these famous stellar nurseries that dominate the local interstellar landscape are arranged on the bubble's perimeter. They owe their existence to the same supernova blasts that cleared the interior. Star death and star birth connected through the geometry of an expanding shell. Then, in late 2024, the Erecita X-ray telescope produced the first full three-dimensional temperature map of the local bubble. The results revealed asymmetries that no one had predicted. The northern part of the bubble, toward galactic north, is significantly hotter than the southern part. This temperature gradient suggests that more recent supernovae exploded preferentially on one side, reheating the gas unevenly. Even more strikingly, the Erecita data uncovered an interstellar tunnel, a channel of hot, low-density gas extending from the local bubble toward the constellation Centaurus, potentially connecting our bubble to a neighboring superbubble. Additional analysis confirmed a previously suspected tunnel in the direction of Canis Major, linking the local bubble to the Gum Nebula, or an even more distant superbubble called GSH 238 plus 00 plus 09. These tunnels suggest that the local bubble is not an isolated cavity. It is one node in a network of interconnected bubbles, tunnels, and hot gas conduits threaded through the galactic disk. Supernovae in one region blast open a cavity. That cavity expands until it meets a neighboring cavity. Where they touch, tunnels form. Over millions of years, this network creates a foam-like structure within the disk, with hot, low-density bubbles separated by walls and sheets of denser, cooler gas. Some astronomers have described this network as a galactic chimney system, where energy from supernova activity in the disk is channeled vertically through connected bubbles and tunnels, venting hot plasma above and below the midplane into the surrounding halo. The solar system happens to sit inside one of these bubbles, and the tunnels above and below us connect to structures that extend outward through the disk toward the regions we are about to explore. But the local bubble is not the only recently discovered structure reshaping our understanding of the local galactic environment. In January 2020, a team of astronomers led by Catherine Zucker and João Alves announced the discovery of the Radcliffe Wave, a massive sinusoidal chain of dense gas clouds undulating through the galactic disk in the Sun's neighborhood. The discovery was made possible by three-dimensional dust maps constructed from Gaia data, which for the first time allowed astronomers to see the true spatial arrangement of nearby molecular clouds rather than their flattened projection on the sky. The Radcliffe Wave stretches approximately 9,000 light-years in length and passes within roughly 500 light-years of the Sun at its closest point. It consists of interconnected stellar nurseries, including several of the most famous star-forming regions visible from Earth: the Orion Nebula Complex, the Taurus Molecular Cloud, the Perseus Cloud, the North American Nebula, and the Cygnus X Complex. These regions, which astronomers had studied individually for decades, turned out to be connected as segments of a single enormous wave-like structure threaded through the Orion Arm. The wave's shape is remarkable. Viewed from above the galactic plane, it appears as a nearly straight filament stretching across the nearby disk. But viewed from the side, it oscillates sinusoidally, cresting approximately 500 light-years above the galactic midplane and dipping 500 light-years below it, with a wavelength of roughly 6,500 light-years. The wave contains approximately 3 million solar masses of gas and dust, and it appears to be physically oscillating, moving in a pattern consistent with a travelling wave rather than a static structure. A 2024 study confirmed this oscillation, showing that the gas clouds and young star clusters within the wave exhibit coherent vertical motions matching the wave's spatial undulation. The Radcliffe wave replaced an older concept called the Gould belt, a supposed ring of young stars and gas clouds encircling the Sun that had been described since the 19th century. What astronomers had interpreted as a tilted ring surrounding us turned out to be a portion of the Radcliffe wave seen from inside, a straight, sloping segment of the wave that created the illusion of a ring when projected on the sky. The remaining portion of the supposed Gould belt, in the direction of Scorpius and Centaurus, turned out to be an unrelated concentration of gas associated with the loop I bubble. Decades of astronomical interpretation had to be revised once the true three-dimensional geometry was revealed. The cause of the Radcliffe wave remains unknown. Proposed explanations range from the gravitational impact of a dwarf galaxy or massive dark matter clump passing through the galactic disk, to Kelvin-Helmholtz instabilities arising from the relative motion between the disk and the dark matter halo, to Parker instabilities in the galactic magnetic field. None of these hypotheses has been confirmed. A 2025 study from the University of Vienna demonstrated that the solar system's past trajectory intersected the Radcliffe wave in the Orion star-forming region approximately 14 million years ago. During the Miocene epoch, a period that coincides with a significant global climate transition on Earth, the potential link between galactic environment and terrestrial climate remains speculative, but the physical crossing itself is well established by tracing the Sun's orbit backward through reconstructed positions of the wave's constituent gas clouds. Even more recently, in 2025, a study using Gaia data revealed an even larger wave rippling through the Milky Way's disk, spanning tens of thousands of light-years. This great wave was detected through the vertical positions and motions of young giant and Cepheid variable stars across a broad swath of the galaxy. The observed pattern shows stars systematically displaced above and below the midplane in a coherent oscillation, with the stars' vertical velocities offset from their spatial positions in a way consistent with a genuine propagating wave. The origin of this larger wave is also uncertain, though a past encounter or collision with a dwarf galaxy is considered a likely trigger. Its relationship to the smaller Radcliffe wave is unclear, but its existence suggests that the Milky Way's disk is not a static, stable sheet. It is alive with ripples, oscillations and disturbances that give the disk's vertical structure a dynamic, time-varying character. This is the environment the solar system inhabits, not a calm, featureless plane, not a smooth, uniform disk, a dynamically rippling structure punctuated by supernova-blown cavities, threaded with interstellar tunnels, shaped by enormous wave-like oscillations in the gas, and structured vertically into distinct layers with different stellar populations, different chemistry, and different ages. The solar system is embedded within all of this, sitting inside the local bubble near the Radcliffe wave, within the Orion Arm, oscillating slowly through the midplane of a disk that is itself oscillating on much larger scales. Consider what this means for the question at hand. When you ask what exists above and below the solar system, you are not asking about a blank background. You are asking about specific vertical layers of a complex, layered structure. Immediately surrounding the Sun, the local bubble creates an unusually clear vertical corridor. The hot, sparse gas of the bubble extends in all directions, but particularly above and below the disk where the interstellar medium offers less resistance. Moving farther out, you encounter the edges of the thin disk, where the density of young stars and gas begins to drop. Beyond that, the thick disk takes over, populated by older stars moving in broader, more inclined orbits. Beyond the thick disk, the stellar halo begins, a vast, diffuse sphere of ancient stars and globular clusters that extends far above and below the midplane. And beyond even the stellar halo, the dark matter halo stretches outward for hundreds of thousands of light years, invisible but gravitationally dominant. Each of these layers is real. Each has been observed, measured, and mapped. Each contains different objects, different physics, and different histories, and each occupies the vertical dimension, the direction the textbook diagram leaves blank. There is one more detail that completes the framework before we look directly into those vertical spaces. The Milky Way's disk is not perfectly flat, it is warped. Beyond about 40,000 light-years from the galactic center, the outer disk begins to bend, curving upward on one side and downward on the other, like the brim of a hat that has been pushed up on the left and down on the right. This warp has been mapped through radio observations of neutral hydrogen gas and confirmed by stellar surveys. Its cause is debated, with leading explanations including gravitational interactions with the Magellanic Clouds and the torque exerted by a misaligned dark matter halo. The warp does not significantly affect conditions at the Sun's radial position, but it adds another layer of complexity to the galaxy's vertical structure and reinforces the central point. The galactic disk has a rich, detailed, three-dimensional geometry that the flat mental model completely ignores. Additionally, features like the triangular Andromeda ring and the Monoceros ring, stellar overdensities found far above and below the midplane at large galactic radii, hint that the disk's outer regions have been disturbed and wrinkled by interactions with satellite galaxies over billions of years. Stars have been kicked out of the main disk, scattered into structures that rise and fall thousands of light years above and below the midplane, blurring the boundary between the disk and the halo. These features demonstrate that the galaxy's vertical extent is not a clean, well-defined boundary, but a messy, dynamic zone where disk and halo merge in ways astronomers are still working to disentangle. The framework is now in place. You know the solar system's galactic address, 26,000 light-years from the center, within the Orion Arm, roughly 55 light-years above the midplane, inside a supernova-blown cavity called the local bubble, near a 9,000 light-year oscillating gas filament called the Radcliffe wave, embedded in a disk that ripples with larger waves and warps at its outer edges. You know that galactic north points toward Coma Berenices, galactic south toward Sculptor, and that these directions lead out of the disk into vertically layered structures of increasing age, decreasing density, and profoundly different character. What remains is to look directly into those directions and describe, layer by layer, what actually occupies the space above and below the galactic plane from our position. The answer involves ancient stars older than the Earth itself, globular clusters that have been orbiting for billions of years, a gaseous halo heated to millions of degrees, satellite galaxies being slowly consumed, and an ocean of invisible dark matter that outweighs everything visible by a factor of 10. None of it appears on the textbook diagram. All of it is there. Begin at your feet, not literally, but galactically. You are sitting inside the thin disk of the Milky Way, roughly 55 light-years above the midplane, surrounded by the densest concentration of stars, gas, and dust in the galaxy. This is the ground floor, the busy urban core of the galactic disk, where young blue stars ignite inside collapsing molecular clouds, where supernova remnants expand in filamentary shells, where the raw materials of star formation swirl through spiral arms and interarm regions in a slow gravitational current that has been flowing for billions of years. This is the environment you know, or at least the environment the textbooks acknowledge. Now, look upward. Not toward the sky above Earth, but toward galactic north, the direction perpendicular to the Milky Way's midplane, pointing toward the constellation Coma Berenices. What you are about to travel through, layer by layer, is a vertical column of galactic structure that extends far beyond anything most people associate with the words our galaxy. The first few hundred light years above the midplane feel familiar. You are still deep inside the thin disk. Stars surround you in every direction. The interstellar medium, that diffuse ocean of hydrogen gas and microscopic dust grains that fills the space between stars, remains dense enough to scatter and absorb light from distant objects. Molecular clouds, the cold, dark nurseries where new stars form, still appear at irregular intervals. You would not notice any dramatic change if you could somehow travel vertically through this region. The stellar density is dropping, gently and exponentially, but the environment still looks recognizably like the galactic neighborhood you just left. However, the composition of the stars is already shifting in subtle ways. Near the midplane, the stellar population is a mix of all ages. Young blue giants burn ferociously and die within millions of years. Middle-aged yellow stars like the Sun persist for billions. Ancient red dwarfs endure for trillions. The thin disk near the midplane contains this entire range, because star formation has been continuous there for most of the galaxy's history. But as you climb vertically away from the midplane, the youngest stars disappear first. The hot blue giants and the active star-forming regions are concentrated within a remarkably narrow layer, perhaps 300 to 400 light-years thick, centered on the midplane. Rise above that layer, and the interstellar gas thins, the dust clears, and the stellar population shifts toward older, cooler stars. You are leaving the zone where new stars are born and entering a region populated increasingly by stars that formed long ago and have had time to drift vertically away from their birthplace through gravitational interactions. By about 1,000 light-years above the midplane, you have reached the upper boundary of the thin disk. This is not a sharp edge. No wall or barrier marks the transition. The stellar density simply continues its exponential decline, and the character of the surrounding stars continues to evolve. But astronomers identify this altitude as the approximate scale height of the thin disk, the distance at which the density has dropped to roughly 1/3 of its midplane value. Above this point, you enter a different structural component of the galaxy entirely. The thick disk begins here. This is one of the least intuitive features of the Milky Way for people encountering it for the first time, because its name suggests something solid and well-defined, when in reality it is a diffuse, gradually transitioning population of stars that overlaps with the thin disk below and the halo above. The thick disk extends roughly 2,000 to 4,000 light-years above and below the midplane, depending on how the measurement is made and which stellar population is used as a tracer. Its scale height is 3 to 4 times greater than the thin disks, meaning its stars are spread over a much larger vertical range. The stars of the thick disk are different from thin disk stars in nearly every measurable property. They are older, typically 7 to 10 billion years old, meaning they formed when the Milky Way was less than half its current age. They are more metal-poor, containing roughly half the concentration of elements heavier than helium compared to typical thin disk stars near the midplane. Their orbits are different too. Thin disk stars like the Sun orbit the galactic center in nearly circular paths that stay close to the midplane. Thick disk stars follow more eccentric, more inclined orbits that carry them thousands of light-years above and below the midplane on each circuit. This is why they occupy a puffier distribution. They are not hovering stationary above the disk. They are passing through on elongated orbits, spending part of their time above the midplane and part below, like a vast population of galactic commuters whose routes take them far from the metropolitan center. How the thick disk formed remains an active area of research. Several competing hypotheses exist. One proposes that the thick disk formed from the thin disk, with ancient gravitational interactions, perhaps a collision with a dwarf galaxy, heating the orbits of pre-existing thin disk stars and puffing them outward vertically. Another suggests that the thick disk formed separately, from gas that was more turbulent and vertically extended in the early galaxy before the thin disk settled into its current narrow configuration. A third hypothesis invokes radial migration, where stars born in the inner galaxy gradually spiraled outward over billions of years, acquiring more vertical energy in the process and ending up in thicker orbits at larger radii. Observations from the Gaia mission have provided critical data to test these models. The chemical compositions and orbital properties of thick disk stars carry fingerprints of their formation history, and astronomers are painstakingly using those fingerprints to reconstruct events that occurred billions of years in the past. What matters for our vertical journey is this: 2,000 light-years above the midplane, you are immersed in a population of ancient stars that belong to a different epoch of galactic history than the stars near the Sun. These are stars that witnessed the Milky Way in its youth, when the galaxy was still assembling itself through collisions and mergers with smaller systems. They orbit in a broader, more disordered fashion than their thin disk counterparts, and they are surrounded by far less gas and dust. The interstellar medium has thinned dramatically by this altitude. Molecular clouds are essentially absent. The raw material for star formation is gone. No new stars are being born here. The thick disk is a museum, a living archive of the galaxy's early history, populated by ancient survivors drifting through mostly empty space on billion-year-old orbits. To appreciate what this journey would actually feel like, consider what the night sky would look like at different altitudes above the midplane. From Earth's position, deep inside the thin disk, the Milky Way band dominates the sky on clear, dark nights. It is a bright, textured river of light spanning the heavens from horizon to horizon, crowded with stars, punctuated by dark dust lanes, and glowing with the combined luminosity of billions of suns seen edge on through the dense central layer of the disk. Stars crowd every direction along the band, so densely packed in appearance that individual points blur into a continuous glow. Now imagine rising 1,000 light-years above the midplane. The Milky Way band is still visible, but it has changed. It appears narrower and slightly less brilliant, because you are now above most of the dust that scatters and reddens light within the disk. You can see farther along the midplane in every direction, and the dark rifts caused by intervening dust clouds have diminished. But looking away from the band, toward galactic north or galactic south, the sky has grown noticeably darker. Fewer stars populate those directions. The rich stellar fields that surrounded you at the midplane are thinning, giving way to isolated points of light separated by wider and wider gaps of blackness. Rise to 5,000 light-years. Now the disk is far below you, and looking back toward the midplane, you see something astonishing. The Milky Way is no longer a band across your sky. It is a luminous sheet stretching beneath you in every horizontal direction, glowing with the collective light of hundreds of billions of stars compressed into a structure thin enough to see nearly edge on from your elevated vantage point. The spiral arms are visible as brighter concentrations within the sheet, curving away from a brilliant central bulge that dominates the inner region. Above you, the sky is almost perfectly black. The halo stars surrounding you are so sparse that the nearest one might be dozens or hundreds of light-years away. You are alone in a way that no human being on Earth has ever experienced, surrounded by a volume of space so empty that the galaxy below you provides virtually all the light in your sky. Continue to 50,000 light-years above the midplane. The Milky Way is now a complete object below you, a glowing spiral galaxy seen from outside, its disk foreshortened into a luminous band, with spiral arms trailing away from a bright bar-shaped core. The galaxy appears roughly the size of your outstretched hand held at arm's length. You are farther above the disk than the disk is wide. Individual stars are invisible at this distance. What you see is the integrated glow of the entire stellar population, concentrated in the disk and bulge, fading into the diffuse outer regions. Around you, the stellar halo is so sparse that only the nearest globular clusters and the brightest individual stars are detectable. The Magellanic Clouds are visible off to one side, two glowing patches of light orbiting the galaxy at distances comparable to your own. The rest of the sky is dominated by the blackness of intergalactic space, punctuated by the faint smudges of distant external galaxies millions of light years beyond the Milky Way. This progression from immersion in the bustling midplane to solitary observation of the galaxy from above unfolds entirely within the vertical dimension, the same dimension that the textbook diagram leaves blank. Every altitude tells a different visual story, and every visual story corresponds to a different physical environment with different stellar populations, different densities, and different histories. Continue upward, beyond roughly 4,000 to 5,000 light-years above the midplane. The thick disk fades into something even more diffuse, even older, even stranger. You have entered the stellar halo. The stellar halo of the Milky Way is a vast, roughly spherical distribution of stars, stellar streams, and globular clusters that envelops the entire disk. Its stars are among the oldest objects in the galaxy, many of them exceeding 12 billion years in age, formed when the universe itself was less than 2 billion years old. Their chemical compositions reflect this extreme antiquity. They are profoundly metal-poor, some containing less than 1/100th the concentration of heavy elements found in the Sun. A few are so chemically primitive that they may be only 1 or 2 generations removed from the very first stars that ever formed in the universe. The stellar halo extends to extraordinary distances. Observations confirm halo stars at distances exceeding 100,000 light-years from the galactic center, with some detections reaching 150,000 light-years or more. The total number of stars in the halo is small compared to the disk, perhaps 1 to 2% of the Milky Way's total stellar population, but they are spread across an enormous volume, occupying a roughly spherical region that dwarfs the thin, flat disk in three-dimensional extent. If you could see the Milky Way from outside and somehow highlight only the halo stars, the galaxy would not look like a flat disk at all. It would look like a faintly glowing ball with a brighter stripe through the middle. The Gaia mission has been transformative for understanding the halo, and one of its most significant discoveries reshaped the history of the inner halo entirely. By measuring the precise positions, velocities, and chemical compositions of millions of halo stars, astronomers identified a vast population of stars on distinctive, highly eccentric orbits concentrated in the inner halo, within roughly 60,000 light-years of the galactic center. These stars share similar chemical signatures and orbital properties that set them apart from other halo populations. They are the debris of a single massive collision, the Gaia-Enceladus merger. Approximately 10 billion years ago, the young Milky Way collided with a substantial dwarf galaxy, roughly 1/4 the mass of the Milky Way at that time. This was not a grazing flyby. It was a direct merger, a prolonged gravitational absorption that dismantled the incoming galaxy entirely. The stars of Gaia-Enceladus were scattered into the Milky Way's halo, where they continue to orbit on trajectories that preserve the memory of that ancient collision. Many move on retrograde orbits, circling the galactic center in the opposite direction from the disk's rotation, a telltale signature of extragalactic origin. Others follow radial, plunging orbits that carry them from the outer halo deep into the inner galaxy and back again. The discovery of Gaia-Enceladus fundamentally changed the story of the stellar halo. What astronomers had previously thought of as a diffuse, ancient population of stars formed within the proto-Milky Way turned out to be largely composed of immigrants. Perhaps half or more of the inner halo stars are Gaia-Enceladus debris. When you look above and below the galactic disk into the halo, a substantial portion of the stars you encounter are not native to the Milky Way at all. They are remnants of a galaxy that no longer exists, absorbed and dispersed so thoroughly that only their orbital and chemical fingerprints reveal their true origin. Scattered through the halo alongside these individual ancient stars are the globular clusters, and these are among the most remarkable objects you would encounter on this vertical journey. A globular cluster is a gravitationally bound sphere of stars, typically containing 100,000 to 1 million stars packed into a volume only a few dozen light-years across. The stars are so closely spaced that near the cluster center, The average distance between neighboring stars is only a fraction of a light year, tens of times closer together than the stars in the Sun's neighborhood. If you could stand on a planet inside a globular cluster, the night sky would blaze with thousands of visible stars, many of them brighter than Venus appears from Earth. The Milky Way hosts approximately 150 known globular clusters, and the true number may be somewhat higher, with additional faint or heavily obscured clusters awaiting discovery. These clusters orbit the galactic center on long elliptical paths that carry them far above and below the disk. Some clusters have orbits that take them tens of thousands of light years from the midplane. Others plunge through the disk on nearly radial trajectories, passing through the dense central regions before climbing back into the halo. Their distribution is roughly spherical, concentrated toward the galactic center but extending in all directions, including directly above and below the Sun's position in the disk. The ages of globular clusters place them among the oldest structures in the Milky Way. Most have ages between 10 and 13 billion years, meaning they formed during or shortly after the galaxy's initial assembly. Some may be remnants of smaller galaxies that the Milky Way absorbed during its early growth. Others may have formed within the proto-Milky Way itself, from gas that had not yet settled into the thin disk. Their extreme ages and chemical poverty make them time capsules, preserving information about conditions in the universe when the first large galaxies were just beginning to coalesce from the primordial gas. Looking upward from the Sun's position toward galactic north, you would eventually see individual globular clusters passing overhead on their orbital trajectories, some relatively nearby at distances of a few thousand light years, others immensely far away at 50 or 80,000 light years above the disk. Each one is a self-contained stellar city, a dense knot of ancient stars orbiting through the otherwise sparse halo, like a ship crossing an empty ocean. The contrast between the dense interior of a globular cluster and the near vacuum of the halo surrounding it is among the most extreme density transitions anywhere in the galaxy. The halo also contains stellar streams, the stretched-out remnants of smaller galaxies and star clusters that the Milky Way has gravitationally dismembered over billions of years. These streams are rivers of stars that trace out the orbital paths of their destroyed parent objects, wrapping around the galaxy in long, thin arcs that can extend tens of thousands of light years. The Sagittarius stream, the longest and most studied example, originates from the Sagittarius dwarf galaxy, a small galaxy currently being torn apart by the Milky Way's tidal forces. The stream wraps around the galaxy multiple times, with portions of it passing high above and below the galactic disk. Other streams, like the GD1 stream and the Orphan stream, have been traced to enormous distances in the halo, providing direct evidence that the Milky Way grew partly by cannibalizing smaller systems. Now continue beyond the stellar halo. The stars have thinned to almost nothing. Individual halo stars still appear at intervals of thousands of light years, but the dominant component of the galaxy at these distances is no longer visible to any conventional telescope. You have entered the domain of the gaseous halo, and beyond it, the dark matter halo. The gaseous halo of the Milky Way is a massive reservoir of hot, ionized gas that extends well beyond the stellar disk. Observations from X-ray telescopes including Chandra, XMM Newton, and Suzaku have confirmed the presence of gas heated to temperatures between 100,000 and several million degrees Kelvin, distributed in a roughly spherical configuration around the galaxy. This gas is extremely tenuous, far less dense than the interstellar medium within the disk, but it occupies such an enormous volume that its total mass is substantial. Estimates vary, but the gaseous halo may contain as much as 10 billion solar masses of hot plasma, a significant fraction of the galaxy's total baryonic content. This hot halo gas plays a critical role in the galaxy's evolution. It represents a reservoir of material that can cool, fall inward, and eventually fuel future star formation in the disk. It also serves as the medium through which satellite galaxies move, creating drag that gradually slows their orbits and facilitates their eventual absorption by the Milky Way. The interaction between satellite galaxies and the hot halo gas strips material from the smaller systems, creating tails and wakes of gas that astronomers can detect. But the gaseous halo is not a quiet, homogeneous bath of hot plasma. It is punctuated by dramatic structures and raining within falling material. One of the most significant populations of objects in the vertical space above and below the disk are the high-velocity clouds. These are massive concentrations of neutral hydrogen gas detected by radio telescopes, moving at velocities that are incompatible with the normal rotation of the galactic disk. Some are falling toward the disk from above, others approach from below. Their speeds range from roughly 70 to more than 400 kilometers per second relative to the local standard of rest. They carry masses ranging from a few hundred to several million solar masses, and their origins are varied and debated. Some high-velocity clouds are thought to be condensations within the hot gaseous halo, regions where the million-degree plasma has cooled enough to form neutral hydrogen that then falls inward under gravity. This process is part of a larger phenomenon called the galactic fountain, and it transforms the vertical column above and below the disk from static scenery into an active circulatory system. The cycle works like this. Deep in the disk, massive stars live fast and die violently, detonating as supernovae that blast hot gas upward through the thin disk at tremendous speed. This gas, heated to millions of degrees, rises through chimneys and bubbles, the same structures we explored in the local bubble, and erupts into the space above and below the midplane. As it rises, it expands, cools, and decelerates. Eventually, gravity wins. The gas condenses into clouds of neutral hydrogen that fall back toward the disk, gaining speed as they descend. These returning clouds slam into the disk's gas layer, triggering shock waves that compress the surrounding medium and can in turn initiate new episodes of star formation. The galactic fountain means the vertical column above and below the solar system is not a static inventory of old stars and invisible mass. It is a living pipeline. Material is constantly being ejected upward from the disk, processed through the halo, and returned. The timescale of one complete fountain cycle, from supernova explosion to cloud return, is estimated at roughly 100 million years. At any given moment, billions of solar masses of gas are somewhere in this cycle, distributed across a range of altitudes above and below the midplane in various states of heating, cooling, condensation, and infall. The space above your head is not just populated, it is circulating. Other high-velocity clouds may have a more exotic origin. Some appear to be fragments of gas stripped from satellite galaxies, particularly the Magellanic Clouds. The Magellanic Stream, an enormous ribbon of neutral hydrogen trailing behind the large and small Magellanic Clouds, arcs across more than 100 degrees of the sky and extends roughly 300,000 light-years in length. This stream is one of the most prominent features in the vertical environment around the Milky Way. It was torn from the Magellanic Clouds by tidal forces and ram pressure as these satellite galaxies orbit through the Milky Way's hot gaseous halo. Portions of the Magellanic Stream pass high above and below the galactic disk, and individual fragments of the stream appear as high-velocity clouds when observed in radio surveys. They represent material in transit, falling from the halo toward the disk, where they will eventually be incorporated into the galactic gas supply and potentially form new stars. The Magellanic Clouds themselves are among the most prominent objects at high galactic latitude. The Large Magellanic Cloud, containing roughly 30 billion stars, orbits at approximately 160,000 light-years from the Sun. The Small Magellanic Cloud, with roughly 7 billion stars, accompanies it at approximately 200,000 light-years. Both are visible to the naked eye from the southern hemisphere, appearing as detached patches of the Milky Way. They are connected to the galaxy by the Magellanic Stream trailing behind them, and a leading arm of gas extending ahead of their orbital path. Together, the Magellanic System represents the most dramatic ongoing interaction between the Milky Way and its satellite environment, a process playing out directly above and below the galactic disk. One of the most dramatic features associated with the gaseous halo are the E Rosetta bubbles, enormous structures of hot gas extending above and below the galactic center. These bubbles, detected by the Rosetta X-ray telescope, span roughly 70,000 light-years in total vertical extent, making them even larger than the Fermi bubbles, gamma-ray emitting lobes previously discovered by the Fermi Space Telescope. The Fermi bubbles extend approximately 25,000 light-years above and below the galactic center. Their edges are remarkably sharp, suggesting they are bounded by shock waves propagating outward into the surrounding halo gas. The energy required to inflate structures this large is enormous, equivalent to the output of millions of supernovae, and the leading explanations involve either a past episode of intense activity from the supermassive black hole Sagittarius A star at the galaxy's core, or an extreme starburst event in the central molecular zone surrounding the black hole. The Fermi bubbles and Rosetta bubbles demonstrate something critical about the vertical dimension of the galaxy. The space above and below the disk is not passive. It is not simply empty volume waiting to be catalogued. It is an active zone where energy generated in the disk is transported outward, inflating vast cavities, driving shockwaves through the halo gas, and reshaping the circumgalactic environment on scales of tens of thousands of light-years. While the Sun does not sit directly beneath the Fermi bubbles, their existence proves that the galactic vertical is a dynamic, energetic dimension, not the quiet emptiness that intuition suggests. Beyond the gaseous halo, the dark matter halo dominates. Dark matter constitutes approximately 85% of all matter in the Milky Way by mass, and its distribution defines the true gravitational extent of the galaxy. The dark matter halo is roughly spherical, extending to distances that recent studies estimate at approximately 300,000 parsecs, or roughly 1 million light-years, from the galactic center. At this distance, the Milky Way's gravitational influence gives way to the intergalactic medium and the gravitational domains of neighboring galaxies. The dark matter halo cannot be observed directly. Dark matter does not emit, absorb, or reflect electromagnetic radiation. Its presence is inferred entirely from gravitational effects. The rotation speeds of stars and gas in the outer galaxy, the orbital velocities of satellite galaxies, the gravitational lensing of light from more distant objects, and the dynamics of stellar streams whose paths are shaped by the total gravitational potential they orbit within. Every one of these measurements points to the same conclusion. The Milky Way is embedded within a vast cocoon of invisible mass that outweighs all the visible stars, gas, and dust by a factor of roughly 10 to 1. The shape of the dark matter halo is not perfectly known. Models suggest it may be slightly oblate, flattened in the same direction as the disk, or possibly triaxial, with 3 different dimensions. Recent studies using stellar streams and satellite galaxy orbits have attempted to constrain the halo's shape, but results vary depending on the data and modeling techniques used. A 2020 study estimated the edge of the Milky Way's dark matter halo at approximately 292 kiloparsecs from the center, plus or minus 61 kiloparsecs, translating to a diameter of roughly 1.9 million light-years. What is clear is that the halo extends symmetrically above and below the galactic midplane to distances that dwarf the disk, the thick disk, and the stellar halo combined. If the visible Milky Way is a thin coin, the dark matter halo is the room the coin sits in. Within this dark matter halo orbit the Milky Way's satellite galaxies. More than 60 satellite galaxies have been identified, ranging from the large Magellanic Cloud to ultra-faint dwarf galaxies containing only a few thousand stars and barely detectable against the foreground of Milky Way stars. These satellites are distributed roughly spherically around the galaxy, though some analyses suggest they may preferentially occupy a plane or a few preferred orbital orientations, a finding that has generated debate about whether the distribution is consistent with standard dark matter models. They orbit within the dark matter halo, their trajectories shaped by the invisible gravitational potential that envelops the entire system. Several of these satellite galaxies are located at high galactic latitudes, meaning they are positioned far above or below the galactic midplane. The Sculptor dwarf galaxy, for example, lies in the direction of galactic south at a distance of roughly 260,000 light-years. The Draco dwarf galaxy sits toward galactic north at approximately 260,000 light-years. These are among the objects you would encounter if you could travel directly upward or downward from the solar system's position, out through the disk, through the halo, and into the distant reaches of the dark matter envelope. Some of these satellite galaxies are in the process of being destroyed. The Sagittarius dwarf elliptical galaxy, currently located on the far side of the galactic center at a distance of roughly 70,000 light-years, is being torn apart by the Milky Way's tidal forces. Its stars are being stripped away into the Sagittarius stream, which wraps around the galaxy and passes through regions both above and below the disk. This is galactic cannibalism in progress, the ongoing growth of the Milky Way through the absorption of smaller systems. This is what occupies the vertical column of space above and below the solar system. From the dense midplane outward, the thinning stellar populations of the thin disk, the ancient stars of the thick disk, the sparse and venerable inhabitants of the stellar halo, with their globular clusters and stellar streams, the infalling high-velocity clouds raining neutral hydrogen toward the disk, the vast, hot, gaseous halo detected in X-rays, the galactic fountain-cycling material between disk and halo, the Magellanic Stream arcing across the sky, the Fermi and Erossiter bubbles venting energy from the galactic center, and finally the dark matter halo stretching to nearly 1 million light-years, populated along the way by satellite galaxies being slowly consumed. Each layer is less dense than the one before. Each is older, each extends farther, and each is as physically real as the ground-level disk that textbook diagrams confine you to. The total vertical extent of the Milky Way, measured from the farthest edge of the dark matter halo above the midplane to the farthest edge below, may approach 2 million light-years. 2 million light-years in the vertical direction alone. For a galaxy whose visible disk is only 1,000 light-years thick, the ratio is staggering. The structure you never see in the flat diagram is 2,000 times taller than the disk it surrounds, and all of this has been measured. All of it has been observed, mapped, and confirmed through decades of painstaking work using instruments that see in wavelengths the human eye cannot detect, X-rays for the hot gas, infrared for the dust-obscured stars, radio for the neutral hydrogen and the high-velocity clouds, gamma rays for the Fermi bubbles, and the precise positional measurements of Gaia for the motions and distances of billions of individual stars. The picture is not speculative, it is data. The vertical structure of the Milky Way is one of the most thoroughly documented features of the galaxy, and yet it remains one of the least communicated truths in popular astronomy. What the textbook diagram calls empty space is not empty at all. It is the largest and most massive component of the galaxy you live in, and it extends directly above your head and directly beneath your feet, in directions that no classroom poster has ever thought to label. Something has changed and it cannot be undone. You now carry a piece of information that fundamentally conflicts with the mental image of the solar system that has lived in your head since childhood. The flat diagram with its neat concentric orbits and its black, featureless background is still there in your memory. You can still summon it, but it no longer functions the way it used to. It has been broken open, and through the crack you can see something the diagram was never designed to show, a vertical column of galactic structure, extending above and below your position, layered and ancient and enormous, filled with objects and environments that the diagram's blank background taught you did not exist. This is not a minor correction. This is not like learning that Pluto was reclassified or that Saturn's rings are younger than previously thought. Those are updates to the diagram. What has happened here is a failure of the diagram itself. A recognition that the most basic visual framework people use to understand where they are in space was not just simplified, but actively misleading about the nature of cosmic location. The diagram told you that the solar system was a self-contained arrangement floating in directional nothingness. The truth is that the solar system is an embedded object inside a three-dimensional galactic structure where direction, position, and vertical distance all carry physical meaning. Let that distinction settle for a moment, because it is the entire point. The shock is not that globular clusters exist above the disk. Astronomers have known about globular clusters for over a century. The shock is not that dark matter extends for hundreds of thousands of light years. Cosmologists have modelled dark matter halos for decades. The shock is not any individual object or structure that has been revealed so far. The shock is that all of these things exist in directions that your mental model of the solar system had permanently labelled as empty, and that this mislabeling was not an innocent omission, but a fundamental distortion of what it means to have a location in the galaxy. What makes this distortion so persistent is that it was never corrected by the history of discovery itself. The vertical dimension of the Milky Way has been revealing itself to astronomers for more than a century, and at every stage the revelation expanded the galaxy's vertical reach far beyond what anyone had previously imagined. Yet each discovery stayed confined to specialist literature, never reaching the popular imagination forcefully enough to shatter the flat diagram. The story begins in 1918, when the American astronomer Harlow Shapley made one of the most consequential observations in the history of astronomy. Shapley studied globular clusters, those dense, ancient spheres of stars that orbit the galaxy in the halo. At the time, astronomers believed the Sun was near the center of the Milky Way. Shapley noticed something crucial. The globular clusters were not distributed evenly across the sky. They clustered preferentially in one direction, toward the constellation Sagittarius. More importantly, many of them sat far above and below the galactic plane, scattered through a volume that was clearly spherical and clearly not centered on the Sun's position. By mapping the three-dimensional positions of globular clusters, Shapley was literally mapping the vertical structure of the galaxy, and the result was revolutionary. The globular clusters defined a sphere centered not on the Sun, but on a point roughly 25,000 light-years away in the direction of Sagittarius. The Sun was not at the center of the galaxy. It was out in the suburbs, embedded in the disk, while the globular clusters arced high above and below, orbiting a distant galactic center that the Sun merely circled. The first major insight from looking above and below the galactic plane was that the solar system was not where anyone thought it was. Shapley's discovery decentered the Sun within the galaxy in the same way that Copernicus had decentered the Earth within the solar system. And like the Copernican revolution, it was resisted, debated, and eventually accepted. But notice what happened next. The globular clusters that Shapley used as his tool were objects above and below the galactic midplane. The very act of recognizing the galaxy's true structure required looking vertically, out of the disk, into the halo. The vertical dimension was not a footnote to galactic astronomy. It was the key that unlocked the galaxy's architecture. In the decades that followed, the story expanded. By the mid-20th century, astronomers had identified two distinct stellar populations in the galaxy. Population I stars, young, metal-rich, concentrated in the thin disk. Population II stars, old, metal-poor, found in the halo and globular clusters. This classification, developed by Walter Baade in the 1940s, was essentially a vertical distinction. Population I lived near the midplane. Population II lived above and below it. The galaxy was not just a flat disk. It had a vertical dimension populated by a fundamentally different kind of star. Then came the discovery of dark matter. In the 1970s, Vera Rubin and Kent Ford measured the rotation speeds of stars in the outer regions of galaxies and found them moving far too fast to be held in orbit by the visible mass alone. Something invisible was providing extra gravity. That something turned out to be the dark matter halo, a vast spherical structure extending far above and below the disk in every direction. In a single stroke, the vertical extent of the galaxy expanded from tens of thousands of light years, the range of the stellar halo, to hundreds of thousands of light years, perhaps approaching 1 million. The galaxy had grown vertically by an order of magnitude, and most of that new volume was invisible. The thick disk was proposed in the 1980s and confirmed through stellar surveys in the decades that followed. The local bubble was theorized in the 1970s and mapped in 3 dimensions only in the 21st century. The Radcliffe wave was discovered in 2020. The Eurosita bubble maps were published in 2024. The Gaia-Enceladus merger was identified in 2018. Each discovery added another layer, another structure, another chapter to the vertical story of the galaxy, and each one made the flat diagram look more inadequate than before. Yet through all of this, the textbook diagram never changed. The solar system continues to be drawn as a flat set of orbits against a black background, as though the century of vertical discoveries had never happened. The disconnect between what astronomers know and what the public imagines remains almost total. Think about what the word location actually implies. On Earth, your location is defined by coordinates on a surface, latitude and longitude, but also by context. You are in a city, on a continent, in a hemisphere. You are at a particular altitude. You are surrounded by specific terrain, climate and geography. Your location is not just a point on a map. It is an environment with properties that change depending on which direction you look and how far you travel. If someone described your location by giving you latitude and longitude, but told you nothing about the terrain, the climate, the elevation, or the surrounding geography, you would say the description was incomplete, technically correct but functionally useless. The flat solar system diagram does exactly this. It gives you a positional layout of planets around a star, which is technically correct, but it strips away every piece of contextual information about the galactic environment in which that system exists. It removes the terrain, it removes the altitude, it removes the surrounding geography. It leaves you with a dot on a blank page and calls it a complete picture. And because most people never encounter a more complete picture, the blank page becomes their permanent understanding of cosmic context. The solar system is here. Everything else is darkness. There is no meaningful structure in any direction. There is certainly nothing meaningful above or below. This failure of context is not unique to the solar system diagram. It reflects a deeper problem with how human beings conceptualize space at galactic scales. The problem is not stupidity. It is not a lack of education. It is a genuine cognitive limitation rooted in how human spatial reasoning works. Human brains evolved to navigate 3-dimensional environments on Earth's surface, environments where gravity defines a consistent vertical axis, where the ground provides a reference plane, and where the relevant spatial scales range from arm's length to the horizon. These navigation instincts are powerful and efficient for their intended purpose. They are disastrously inadequate for understanding galactic structure. When a person tries to imagine the Milky Way, their brain reaches for familiar spatial metaphors. A disk is like a plate. The solar system is like a ball bearing sitting on that plate. Above and below the plate is air, empty space, nothing in particular. This metaphor feels natural and intuitive, and it is wrong in almost every way that matters. The disk is not solid. It is a density gradient. The solar system is not sitting on top of it. It is embedded within it, slightly off-center vertically. The space above and below is not empty air. It is structured, layered, and physically consequential, and the transition from disk to halo is not like the edge of a plate. It is a gradual, continuous change in stellar population, density, chemistry, and age that unfolds over thousands of light years without any clear boundary. Every element of the intuitive metaphor fails. The plate has an edge, the galaxy does not. The ball bearing is separate from the plate. The solar system is part of the disk. The air above and below the plate is uniform and featureless. The galactic halo is structured and ancient. The metaphor is not just imprecise. It is structurally incompatible with the reality it is trying to represent. And yet it persists in people's minds because the human brain has no better template for a rotating disk of matter 100,000 light years across. This is where the real cognitive challenge lies. The difficulty is not absorbing individual facts. You can memorize the scale height of the thin disk, the age of thick disk stars, the distance to the nearest globular cluster, the estimated extent of the dark matter halo. Memorizing facts is straightforward. The difficulty is replacing the intuitive picture, the plate and ball-bearing mental model, with something that actually captures the three-dimensional, layered, gradient-rich, boundary-free reality of the galactic environment. This requires not just adding information, but fundamentally restructuring how you imagine the solar system's place in space. Consider what a properly contextualized mental model would look like. Start with the Sun, a single star among hundreds of billions. It orbits the galactic center once every 230 million years. It oscillates vertically through the disk, currently sitting about 55 light-years above the midplane and moving upward. It is embedded inside a hot, low-density cavity called the local bubble, cleared by supernovae over the past 20 million years. That cavity sits within the Orion Arm, near a 9,000 light-year undulating filament of star-forming gas called the Radcliffe Wave. The Orion Arm is one feature within a disk that is approximately 1,000 light-years thick near our position, surrounded by a puffier, thick disk of ancient stars extending 2,000 to 4,000 light-years above and below the midplane. Beyond the thick disk, a spherical stellar halo of extremely old, metal-poor stars and roughly 150 globular clusters extends to at least 150,000 light-years. Beyond that, a gaseous halo of million-degree plasma fills a comparable volume, and beyond everything visible, a dark matter halo stretching to perhaps 1 million light-years defines the true gravitational extent of the Milky Way. In this model, the solar system is not a centerpiece. It is not a focal point around which everything else is arranged. It is a tiny, misimagined detail inside a structure of staggering vertical complexity. Looking up from the Sun toward galactic north is not looking into void. It is looking through layers of progressively older, sparser, and more ancient material, each layer representing a different era of galactic history, each extending farther than the one beneath it, like geological strata in a cliff face that rises for hundreds of thousands of light years. This reframing matters because it changes the fundamental relationship between the observer and the observed. In the flat diagram model, the solar system is the subject, and everything else is background. You stand at the center and look outward into darkness. In the galactic context model, the solar system is one embedded particle inside a vast structure, and the structure is the subject. You are not looking outward into nothing. You are looking outward through something, through layers that are older, wider, and more massive than the thin disk you inhabit. The Gaia mission has made this reframing possible in a way that was not achievable even 20 years ago. Before Gaia, astronomers knew the broad outlines of galactic structure, the disk, the halo, the bulge, but the detailed three-dimensional positions and motions of individual stars were available for only a tiny fraction of the stellar population. Mapping the vertical structure of the galaxy was like trying to understand the architecture of a building by examining a few bricks. Gaia changed that by measuring the precise positions, distances, and velocities of more than 1.5 billion stars, providing for the first time a truly three-dimensional census of the stellar populations in and around the disk. With Gaia data, astronomers could separate thin disk stars from thick disk stars based on their orbits and chemistry. They could trace stellar streams through the halo with enough precision to reconstruct the orbits of the destroyed galaxies that produced them. They could detect the Radcliffe Wave, identify the Gaia-Enceladus merger debris, and map the vertical oscillations of stellar populations across the disk. The eRosita X-ray telescope added another dimension by mapping the hot gas that fills the local bubble, revealing its temperature gradients, its asymmetric shape, and the interstellar tunnels connecting it to neighboring superbubbles. These observations demonstrated that the vertical direction above and below the disk is not merely populated by ancient stars. It is actively shaped by energy flowing outward from the disk, carried by supernova-heated plasma that vents through chimneys and tunnels into the halo. Together, these instruments have given humanity its first genuinely three-dimensional portrait of the local galactic environment. And that portrait looks nothing like the flat diagram. It is messy, layered, dynamic, and deeply structured in the vertical dimension. The galaxy is not a thin sheet of stars surrounded by emptiness. It is a complex, multi-layered system where the vertical extent is hundreds of times greater than the disk's thickness, where each vertical layer contains a different population of objects with a different history, and where the boundaries between layers are gradual transitions rather than sharp edges. This understanding is still evolving. Future missions will refine the picture further. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA, will survey large areas of the sky in infrared, detecting faint halo stars and distant satellite galaxies that current surveys miss. The Vera C. Rubin Observatory, with its unprecedented wide-field survey capability, will discover stellar streams, ultra-faint dwarf galaxies, and transient events in the outer halo that reveal the dynamics of the dark matter potential. Each new discovery will add vertical detail to the galactic model, extending the mapped structure farther above and below the disk, resolving finer features in the thick disk and halo, and connecting the local environment more precisely to the galaxy's global architecture. But even with current data, the core message is clear. The directions that the textbook diagram leaves blank are not blank. They are the largest, most massive, and in many ways most important dimensions of the galaxy. The dark matter halo alone contains roughly 10 times more mass than all the stars, gas, and dust in the visible disk combined. The old stars of the halo and thick disk preserve the earliest chapters of the Milky Way's history, chapters that are inaccessible from studying the thin disk alone. The hot gaseous halo represents a critical reservoir of material that will fuel or fail to fuel future star formation. The satellite galaxies orbiting through the halo are the building blocks from which the Milky Way assembled itself and is still assembling itself today. Strip away the vertical dimension, and you lose not just a few interesting objects. You lose the majority of the galaxy's mass, the majority of its history, and the majority of its future. There is something profoundly humbling about this realization, and it goes beyond the usual platitudes about human smallness. It is easy to say that the universe is big and humans are small. That statement has been repeated so often that it has lost most of its emotional impact. What is harder to absorb, and what this story has been building toward, is the more specific and more unsettling version of that idea. It is not just that the universe is big, it is that even our own immediate galactic neighborhood is structured in ways that our most basic mental models fail to capture. We are not making errors about distant quasars or the edge of the observable universe. We are making errors about the space directly above and below us, the directions that should feel closest and most familiar, because they originate from where we are right now. The flat diagram does not fail because it omits distant objects. It fails because it misrepresents the local reality. The solar system is not floating in a void. It is sitting inside a layered structure, so large that light from its outer regions requires hundreds of thousands of years to reach us. That structure extends in directions that human intuition labels as empty. And those directions contain more mass, more history, and more physical significance than the thin sheet of disk the solar system is embedded within. Picture the situation clearly one final time. You are on Earth, orbiting the Sun, which orbits the Milky Way's center every 230 million years. Right now, in this instant, you are 55 light-years above the galaxy's midplane, rising slowly at a few kilometers per second, inside a hot bubble carved by dead stars, near a wave of star-forming gas thousands of light-years long. Below you, the galactic midplane teems with molecular clouds, young stars, and interstellar dust. Above you, the thin disk gives way to the thick disk, then to the stellar halo with its globular clusters and rivers of stolen stars, then to the gaseous halo glowing in X-rays, and finally to the dark matter halo that extends outward for nearly 1 million light-years in every direction. The same structure exists below you, mirrored on the other side of the midplane, stretching toward galactic south, with the same layers, the same transitions, the same depth. You are not at the center of this structure. You are not at the top or the bottom. You are inside it, embedded near the midplane, in one of the densest layers, surrounded above and below by progressively sparser, older, and more massive envelopes that extend outward to distances that dwarf the visible disk by orders of magnitude. You are a passenger on a star that is bobbing gently through 1,000 light-year thick sheet of gas and young stars, inside a galaxy whose true vertical extent stretches 2,000 times farther than that sheet in both directions. Nothing about this picture was hidden or secret. Every component has been known to astronomers for years or decades. Shapley mapped the globular cluster distribution in 1918. Baade identified the two stellar populations in the 1940s. Rubin measured the dark matter halo's influence in the 1970s. The thick disk was confirmed in the 1980s. The local bubble has been studied since the 1970s. The Radcliffe wave was discovered in 2020. The Gaia-Enceladus merger was identified in 2018. The eROSITA bubble maps were published in 2024. None of this is new in the sense that it surprised the scientific community. What is new, or at least what should feel new, is the synthesis, the act of putting all of these components together and pointing them in the same direction, the vertical direction, the direction the textbook diagram never shows, and realizing that what fills that direction is not emptiness but the overwhelming majority of the galaxy's structure. The real answer to the question posed in the title is not a single dramatic object. There is no alien megastructure above the solar system. There is no cosmic wall below it. There is no hidden entity watching from galactic north. The answer is at once simpler and more profound than any of those fictions. What really exists above and below the solar system is the galaxy itself, layer after layer of it, extending outward through populations of stars that grow older, sparser, and more chemically primitive, with every 1,000 light-years of altitude, until the stars give way to hot gas, and the hot gas gives way to dark matter, and the dark matter extends outward for a distance that would take light itself nearly 1,000,000 years to cross. The discomfort this produces is not about fear, it is about orientation. Human beings rely on mental models to feel located in the world. You know where you are on Earth because you have maps, landmarks, a sense of geography. The flat solar system diagram served a similar function for cosmic location. It gave you a picture, a frame of reference, a sense of placement. But that frame of reference was an illusion. It placed the solar system in a void that does not exist. It suggested that the surrounding space was directionless when it is profoundly directional. It implied that the solar system's neighborhood was empty when it is layered with structures spanning billions of years of galactic history. When you replace that flat diagram with the real three-dimensional picture, you do not just add information, you lose something. You lose the comfortable sense of the solar system as a self-contained place, a tidy arrangement of planets with well-defined boundaries and a simple relationship to its surroundings. In its place, you get something far more honest but far less reassuring. A tiny system of planets orbiting a single average star, embedded in a dense layer of a galactic disk, tilted at 60 degrees to the plane of those planets, surrounded in every vertical direction by structures so vast and so ancient that the entire history of the solar system, all 4.5 billion years of it, fits within a fraction of the age of the oldest halo stars drifting overhead. The textbook diagram was never meant to deceive. It was drawn to explain planetary orbits, and it does that well. But by leaving out the galactic context, by surrounding the solar system with blank darkness, it accidentally created a false cosmology in the minds of millions of people. A cosmology in which the solar system floats alone, in which above and below are meaningless, in which the space surrounding us is uniform and featureless, and extends equally forever in every direction. That cosmology is wrong. The space above and below the solar system is not featureless. It is the deepest, most layered, most massive dimension of the galaxy we live in, and it has been there all along, invisible not because it is hidden, but because no one thought to include it in the picture. The next time you see that flat diagram, the one with the yellow sun and the concentric rings of orbits floating against a pure black background, you will know what the black background is hiding. Not nothing. Not void, not the absence of structure, but the galaxy itself, rising above you and falling below you in layers of stars, gas, dark matter, and time, extending outward in directions that your mental map once told you were empty and that turn out to contain almost everything.